So let's try a question. Let's try and see what happens to this protein on the left when we add these chemicals. The protein on the left is a folded protein, it's an enzyme, and we can measure its activity. The exact protein doesn't matter here, just that we can tell when it's active and when it's not. To this enzyme, we add urea and beta-mercaptoethanol. Afterwards, it turns into this denatured protein that is no longer folded and no longer active. So the question is, why? Can you explain, using the structures of these two chemicals and your knowledge, why does this protein unfold when these chemicals are present? Can you explain how it unfolds? What does each of these chemicals do to it? And can you explain what happens when both chemicals are removed from this solution, when one is removed from the solution, and when one is removed sequentially? For example, if urea is removed first and then beta-mercaptoethanol, what happens to this protein? And when beta-mercaptoethanol is removed first and then urea, what happens to this unfolded protein? Can we get the activity of the enzyme back? Try to use your fundamental knowledge and build logically from there. Speak it out loud, either to the air or other people, and give this question a go. So, do you have an answer? Let's take a look at this in steps. What is the knowledge that you should start with here? So you know there's a protein. Can you describe what's happening here? On the left, our protein is folded, and clearly marked out are these cysteine-cysteine bonds, disulfide bridges, covalent bonds, which are broken in the right-hand side. We just are left with our SH group. So that tells you that at some point, these covalent bonds are broken. Now let's think about your knowledge of protein structure. Why is a protein folded, and what are the forces involved? So the protein structure is in 4 levels. Firstly, you have your primary structure, which is your polypeptide chain. That is the structure on the right. There's a single chain of protein. Then you have your secondary structure. This is your beta sheets and your alpha helices, and these are held together by hydrogen bonding. Thirdly, your tertiary structure. These are held together by ionic bonds, covalent bonds like disulfide bridges, hydrogen bonds, and hydrophobic and hydrophilic interactions. Lastly, you have your quaternary structure. Although, because this is a single polypeptide, quaternary structure does not apply, because quaternary structure is bonding between separate polypeptides. So these are your bonds. These are the only chemical bonds that keep a protein together. So when a protein unfolds, some of these bonds must be disrupted. But how? Let's think about urea first. Urea is a small molecule. It's got a carbon bonded to oxygen, double bonded, and then it has 2 NH2 groups. Can this disrupt any of the bonds we've mentioned? Hydrogen bonds, ionic bonds, covalent bonds, or hydrophobic, hydrophilic interactions? In fact, it can disrupt hydrogen bonds, and it's very potent at disrupting hydrogen bonds. So then think back to what you know about hydrogen bonds. Hydrogen bonds are formed when you have a delta positive hydrogen, when a hydrogen has more positive charge than negative. And this is because it's bonded to an electronegative atom. For example, oxygen. Oxygen is electronegative. It draws the electrons in a covalent bond towards it, which makes it delta negative, slightly negative, and makes the hydrogen bonded to it slightly positive. In this example, there's two water molecules. When two water molecules get close, they can form a hydrogen bond, an electrostatic bond between the delta negative oxygen and delta positive hydrogen. Let's look at our urea. Can that do the same thing? You can say here that nitrogen is also an electronegative atom. It's next to oxygen on the periodic table, so it should also have the same effect on your hydrogens. Your hydrogens are delta positive, your nitrogens are delta negative. If you have done content on lone pairs already, then you can also explain this by saying nitrogen has 5 electrons in its outer shell. 3 is occupied, 1 for each hydrogen and 1 for the carbon covalent bonds. So it has 2 electrons left, forming a lone pair. And a lone pair is delta negative, and it can also bond with a delta positive hydrogen. You could say that. You could also look at this oxygen. Oxygen is more delta negative than carbon, so it will draw the electrons in that double bond towards it. It is also delta negative, and oxygen also has 2 lone pairs here, just like in water. In fact, it is the oxygen lone pairs that is the delta negative agent in these disruptive actions against hydrogen bonds. The delta negative oxygen will bond to delta positive hydrogens in the protein, and the delta positive hydrogens on the urea will bond to the delta negative elements of the protein, and therefore breaking the hydrogen bonds and causing the protein's denaturation. So then let's think about the next thing, the beta-mercaptoethanol. You've now broken all of the hydrogen bonds in this protein. You can assume perhaps that because the urea is slightly delta negative and delta positive, it might disrupt the ionic bonds too. But the covalent bonds, they are very strong. How would they be disrupted? If your guess was beta-mercaptoethanol is the thing that breaks covalent bonds, then you'd be correct. There's a few clues as to why. You see, cysteine bonds, sulfur-sulfur bonds, they form between 2 sulfur atoms. Beta-mercaptoethanol also has a sulfur atom here at the end. So you might be able to guess that somehow it is involved in bonding to the sulfurs of the cysteines in the protein and preventing them or breaking them from bonding to each other. Maybe if you wanted to go above and beyond, you want to give a chemical mechanism. And this is what happens. The sulfur, like oxygen, it is just one row down beneath oxygen, has lone pairs which can react, is going to attack the sulfur in the sulfur-sulfur bond and break the bond itself. This bond, these electrons, can then pick up a proton from the water, become satisfied, and you have this structure which is your beta-mercaptoethanol bonded to the cysteine, which can then be attacked by another one of the beta-mercaptoethanol to give you 2 cysteines that have been broken, the bond between them was broken, and this kind of waste product where the beta-mercaptoethanol has bonded to each other. This is a mechanism of how this reaction could happen. Although, depending on what you have learnt in A-level so far, I might not expect you to be able to guess at this mechanism. Saying with evidence that the beta-mercaptoethanol is the thing that breaks this sulfur-sulfur bond I think would be enough for me at this moment. But you have to give some reasons of why you think that. And one of the reasons is it's a sulfur-sulfur bonds already exist here. You can feasibly see that this sulfur could sulfur-sulfur bond with one of the sulfurs in the protein. Great. So that is the effects of urea and beta-mercaptoethanol. We can now move on to the more difficult questions. So what do you think will happen when you remove both urea and beta-mercaptoethanol? Do you expect the protein to regain its complete function? Depending on whether you said yes or no, whilst there is a correct answer, what matters is that you have a strong theoretical basis to what you are trying to argue. If you are arguing for no, the protein won't regain all its function, you need to say why you think that. What kind of knowledge is that based in? You could say that perhaps the protein doesn't have enough information to fold back to the way it was. Maybe when it was being made, when it was being synthesized originally, it had some helper proteins. So now when this protein folds without those helper proteins, it will fold and fail. You could say there's no way for the sulfur-sulfur bonds to recombine. Beta-mercaptoethanol in there has broken these bonds. Maybe the reverse reaction is energetically disfavored. Perhaps it won't spontaneously fold at all. If you had said, yes, it will fold back to the original protein, then you also need to provide some theories of why. Perhaps the beta-mercaptoethanol, when removed, does cause the sulfur-sulfur bonds to reform. Perhaps there is something else in the cell that can cause this reforming to happen. Other chemicals that help reform sulfur-sulfur bonds, or other proteins that help refold the protein. As poorly folded protein, misfolded protein does happen from time to time in cells, and they must have some kind of mechanism to restore that. Whatever your answer, as long as you have some sound theoretical ideas, I think would be acceptable. Of course, the correct answer here is it will reform. For this particular protein, it will reform and will work. The original experiment was done and they found that over time the protein regained its reactivity. This they attributed to oxygen in the air causing the oxidation and the remaking of these sulfur-sulfur bonds. Now the next question is, what do you think will happen if we remove urea first from this solution, now that we know that if we remove both of them, that the protein will regain its function? Let's think about that for a second. What happens to the protein? Urea causes the denaturation, breaking of the hydrogen bonds. So removing urea will allow the protein to reform hydrogen bonds. Is this enough to form its shape? That's something that you can argue. Yes. You can argue that hydrogen bonds are the predominant forces in a protein, as there's only a few cysteine-cysteine bonds here. There's only 4. Whereas hydrogen bonds prevails in secondary structure and tertiary structure between many different amino acids and between the side chains of the amino acids as well. So then, if you remove urea first, then you have a folded protein, and then you remove beta-mercaptoethanol, which allows a protein to form those cysteine-cysteine bonds again, and you'll get a protein that does function. What about the reverse? What happens if you've removed beta-mercaptoethanol first and then urea? The correct answer here would be removing beta-mercaptoethanol first may cause misaligned sulfur-sulfur bonds. What happens to this protein when it's in solution? It's not going to stay a single straight line where ends don't touch. It's more likely to exist in a jumble, in a string, like a ball of string, a mess. So if you remove beta-mercaptoethanol, you could cause sulfur-sulfur bonds to form where they shouldn't form. There's 8 sulfur groups, 8 cysteines. So there are many, many different combinations that are the wrong combination. In fact, there are 106 combinations, and only one combination will restore the protein to the correct cysteine bonds. Therefore, if you remove beta-mercaptoethanol first, the wrong bonds will form. And then when you remove urea, the rest of the protein will fold and it will fail because the cysteine-cysteine bonds have now caused the wrong structure to form already. Therefore, would you expect the protein to regain its function? Possibly not. What do you think the percentage chance is that your protein regains its function? This is a little stretch question, but it's around 1%. If 1 out of 106 combinations is the correct combination, then there is a 1% chance that your protein will regain function. You can see there are all of these nitty-gritty details. There are logical steps that you may miss, but that's okay. The interviewers will try and guide you through it if you get stuck. There's a few final things to say. First of all, are you satisfied with your answers? Did you get anywhere close, or did you require hints along the way? Some of the hints could have been, think about whether the sulfur on the beta-mercaptoethanol could be involved in the reaction, or think about what bonds are in proteins and what could disrupt them, or perhaps think about what other agents are in the cell that could be affecting these reactions. That brings me to assumptions. So throughout this whole question, we have been making a few assumptions. Do you know what they are? What do you think would change if the context of the question would be a little bit different? For example, we had not said anything about the identity of the protein. We don't know how it's made in the cell, whether it spontaneously folds or requires a helper to fold it. This could mean very drastic things for this question. If the protein folds spontaneously, then it's more likely to regain its function when these agents are removed. If it requires a helper protein, then it may not. Other things to consider is the environment. Everything in biology and everything in chemistry, and to be honest, most things in science, don't operate in a void. You could say, what happens in a cell? Cells have their own environments. There could be proteins that prevent these kind of misfoldings. There could be chemicals that cause refolding. There's much we don't know about the context of this question. There's also context if this was an experiment outside of the cell. What is the temperature? Temperature can also denature proteins. If you're operating at a high temperature, say on a very warm day, then maybe you won't regain your protein function back, for example. What about the pH? Is that controlled? What time scale is this? Is this happening over the course of minutes or days? There are many assumptions, and if you have any questions for your interviewers, you can ask them to clarify. Not only will that help you with the question in the sense that it will help direct you towards the right direction, but it also shows that you are considering these possibilities, which to make a truly rounded scientist, you must consider everything that surrounds the questions, the scientific questions. You must not assume that everything will be simple, and there may always be some other factors that is affecting your experiments or your questions. Finally, if you do want to further prepare for these questions, you should practice interviews with your teachers, parents, friends. Have them pick some questions. There are many on the internet, and just get used to the feeling of talking out loud and talking your thoughts at the interviewers. Get used to drawing diagrams and building a logical explanation based off what you already know. If you don't know something or haven't been taught something, don't be afraid to say so to the interviewers. They don't exactly know what you have been taught. Many different schools will teach in different order, different courses like A-level and IB will teach different content. So if you don't know something, don't be afraid to say, but don't just leave it there. Take your best guess. You can say, I don't know about these chemicals. I haven't done any chemistry reaction mechanisms, but I do know about proteins, so start with proteins. And if you do want to prepare further, you can always look at textbooks. This is above and beyond and isn't a necessary thing for your preparation, but you can always look at textbooks that are featured in first-year university courses. The examples I have here is molecular biology of the cell for cell biology and biochemistry for all things biochemistry. Find them in your local library, perhaps, or see if you can find a version online. So these textbooks often form the undergrad courses around the UK for many biologists, basically. So if you're curious, take a look. It is at a level of university undergrads, so don't worry if you don't understand everything, but if you are curious, you can take a look, because many of the topics within there are the topics that you will learn at an undergrad course in biology or biochemistry.